Welcome again. In the previous sessions we covered the lock variable solution and the strict alternation solution. In this video we are going to discuss one of the important synchronization mechanism which is easy to use in any programming language, and the synchronization guarantees all the three requirements. So let's start with the Peterson solution. So what are the characteristics of this mechanism? It is again a software solution, means it does not have any dependency on the hardware. The second one is it is again the two process solution. So you can say it is a limitation of this solution or the mechanism. You can only synchronize two processes and not more than two processes if they share some resources. The third characteristic is it can be implemented in user mode, means you can write the program to implement this solution in any programming language such as C, C++, Java, and you do not require any additional support from the kernel. The fourth characteristic is it uses the spin lock concept, means once again as same as we discussed in lock variable solution and strict alternation, we wrote some loop in the entry section. Similarly, we are going to write some loop that will check the condition till it becomes false. So the design of the Peterson solution is quite simple once again. The two processes, let's say P0 and P1, when they want to enter into their critical section, they first have to pass through the entry section code that we are going to design and the exit section code. Let's look at the implementation of this. So to implement this Peterson solution, we need to take some shared variables. So what are these shared variables? First, let's define the true as 1 and false as 0, the two constant variables. There is one additional variable we are going to take, which is the integer term, which is not initialized to any value. There are two variables, integer flag 0 and integer flag 1. Both the flags are initialized to initially false. Flag 0 is going to be used by both P0 and P1. Flag 0 will indicate that the process P0 is interested to enter into critical section, and flag 1 will indicate that the process P1 is interested to enter into its critical section. So at the start of system, I can say when both processes has not arrived yet, both the flags are set to false. So both are not interested at the start. What is the implementation of the entry section? Let's look at the P0's entry section first. The first statement is P0 says that I am setting my flag is equal to true. The next statement is turn. It indicates that it is now P0's turn to enter into critical section. So there are two variables the P0 have to set in the entry section. The next one is the while condition, where we are going to check the two conditions. The first one is whether the other process has set its flag or not. So what is the first condition is flag 1 is equal to true, and the second condition is turn mine, means is turn is equal to 0. If both the conditions are true, means definitely it is the P1's turn to enter into the critical section. So this process have to wait. Alright, let me go ahead. So after that we can put some a programmer can put some any critical section lines of code, and after that the exit section implementation is quite simple. The process have to just say, I am setting my flag to false, means I have crossed the critical section, and that's how, depending on this flag value, when it is set to false, if the other process is waiting, its loop is going to break. Similarly, the logic of the process P1, but exactly opposite. Here the P1 will say flag 1 I am going to set to true, it is my flag, and the turn I am going to set it to 1, indicating that it is my turn now. Similar while loop statement is here also, that is a spin lock or busy waiting line here, a busy waiting statement here. So it will check first what is the first condition in while loop. Is the process P0 set its flag to true? Alright, means flag 0 is equal to true, and is it my turn? Turn is equal to 1. If both the conditions are true, then it has to wait. Otherwise, if any of the condition is false, this loop is going to break. And in the exit section of P1, it says that flag 1 is equal to false, and that's how, depending on this flag 1's false value, the process P0's loop is going to break. Let me take a program counter and execute these two processes P0 and P1 concurrently. So let's start with the process P0 first. So here is the flag 0 is equal to true, so I am going to set it to true. I have denoted in the short here, T stands for true. Let's go ahead. The next statement is turn is equal to 0. When the turn is equal to 0, means it is going to initialize the value to 0. Let's go ahead. While flag is equal to true, what is the condition? Let's say evaluate. What is the flag 1's current value? False. False is equal to true. The condition is false, and the program counter will go ahead. It doesn't matter what is this condition, because first condition is false. There is an AND operator here, and that's how this while loop is not going to jump again to the first statement. It will simply enter into the critical section. Now while it is in the critical section, let's execute the process P1. Let us say flag 1 is equal to true. So the false value will be changed to true. The next statement is turn is equal to 1. So it is going to overwrite the value of turn to 1. The next statement is flag 0, means if other process has already set its flag. We know that process P0 has already entered into critical section. So what is the current value of flag 0? It is true. And that's how true is equal to true. The condition is true. Let's check the next condition. Turn. What is the current value of turn? That is 1. 1 is equal to 1. The condition is again true. Both the conditions are true here. And that's how this while loop is going to loop now. Alright. So here the process P1 is doing the busy waiting. That is a spin lock. Even if you execute both the processes P0 and P1 concurrently, means if you do like flag 0, the first statement of P0, flag 0 is equal to true, preempt the process and give the chance to P1. P1 will say flag 1 is equal to true, preempt this process. Go ahead. Turn is equal to 0. Here turn is equal to 1. So even if you execute the process P0 and P1's instructions one by one, then also you will come to know that only one process is able to enter into critical section. In the lock variable solution and strict alternation, I gave you the assembly code corresponding to the entry section. Here for the Peterson solution, let me tell you that even if you execute this entry section at the assembly level instructions or the binary instructions I can say, then also both the out of both the processes only one is going to enter into the critical section. So that's how I say that the Peterson solution guarantees the first requirement of synchronization mechanism, which is mutual exclusion. Let me go ahead with the process P0. So let's assume that the process P0 comes out of the critical section, and in the exit section it is going to set the flag to false, indicating that its job is over in the critical section. And it comes below and do its other non-critical section work. While it is doing some non-critical section, let's again come back to the process P1 and check. What is the value of flag now? Flag 0. The flag 0 is false. False is equal to true. The condition is false, and that's why this loop is going to break, and now P1 is able to enter into critical section. So as I said, the first requirement of the synchronization mechanism, the mutual exclusion, is guaranteed. Now let's discuss the second requirement, that is progress. Let me take the so let me first tell you what is the progress. Let's revise it. Can any process that comes first into the system enter into the critical section? Is it able to enter into the critical section? That question we need to ask for each process, assuming that it is the only one arrived as of now. So let me again take the same set of program for P0 and P1. Here are the shared variables initialized to the turn is not initialized to any value. That's the initial value is garbage, you can assume. Flag 0 is equal to false and flag 1 is equal to also false. And as of now, let's assume that both the processes has not started their execution, means both processes has not arrived at. Let's assume that the process P0 arrives now and ask, can I enter into the critical section? Let's start the execution of P0 only. Assume that the P1 has not arrived yet. So let me start the execution. Flag 0, it will set to true. Then the turn will be set to 0. Let's check the while condition. Flag 1. What is the flag 1's value? Still false. The other process, isn't it? False is equal to true. The condition is false. And that's why this while loop is going to break and the process P0 enters into critical section. So if process P1 is not arrived, the process P0 is able to enter into critical section. Let's again reset the system. Let me reset all the values to initial values. Assume that no process has arrived, and now assume that the process P1 arrives first. Now again, let's execute the process P1 only. What is the first statement? Flag 1 is equal to true. Go ahead. Next statement is turn is equal to 1. Let's check the condition. What is the value of flag 0? Flag 0 is false. False is equal to true. Condition is false, and this while loop will break, isn't it? And that's how this P1 is also able to enter into the critical section if process P0 has not arrived. You see, there is a clear difference between the strict alternation, the earlier solution I discussed, and this Peterson solution. In the strict alternation, the process P1 was not able to enter into the critical section if it arrives first. But here in the Peterson solution, no matter which process arrives first, P0 or P1, either of the two are able to enter into the critical section. That's how I say that the second requirement, that is the progress, is also guaranteed by the Peterson solution. Let us check the third requirement, the bounded waiting. Let's revise. What is the bounded waiting? If a process is already in the critical section and if another process, some other process is waiting in the entry section, then you have to ask the question to the process which is in the critical section, can you re-enter into critical section even if someone is waiting? Alright. If the process gets the re-entry into the critical section if someone is waiting, then in that case we say that the bounded waiting is not guaranteed. Otherwise it is guaranteed. So let me explain with the help of the same program. Let us again take the same program. All initial values. First let's put the process P0 into the critical section. Alright. So let me straight away execute the process P0's entry section and it enters into critical section. Now while it is doing the job in critical section, let's bring the process P1. So let me bring the process P1, flag 1 is equal to true. So here is the flag value changed to true. Turn is set to 1. Let's go ahead. And we know that once the P0 is in the critical section, it is going to loop. Alright. So here is the loop condition. Now the situation is P0 is in the critical section and P1 is waiting in the entry section. Now let us try to put the process P0 again into the critical section, and depending on that answer, yes or no, whether it is able to enter into critical section or not, we will say that bounded waiting is guaranteed or not. So let me proceed with the process P0. Alright, it comes out of critical section, flag 0 is set to false. So here is the change value to false, and it comes out of critical section. And let me one more time execute the entry section of process P0. So here the flag value 0 is set to true. Alright. See, earlier when it came out of critical section, it was set to false. And one more time I am going to execute the process P0, P0's entry section, and again it is saying to setting the flag 0 to true. Let's go ahead. Turn 0 is equal to 0. So it is going to override the value, whatever be the current value, to 0. Let's check the condition. What is the flag 1's value? It is true. True is equal to true. The condition is true. So the first condition is true. Let's go ahead. What is the second condition? Turn. What is the current value of turn? 0. 0 is equal to 0. Yes. This condition is also true. So both the conditions are true here, and that's why this while loop is going to again check those conditions. In short, I can say that now the process P0 is doing the busy waiting. So it will wait now. So did the process P0 got the entry 2 times even if the process P1 is waiting? The answer is no. And that's why it is a fair chance we are giving to the process P1 that if you are waiting, other process will not enter into the critical section twice. So the bounded waiting condition is guaranteed. Alright. Let me just go ahead. So process P0 is in the loop. While it is in the loop, again let us give the chance to process P1. And what it will do, again it will check the value of flag 0. What is the current value of flag 0? Flag 0 is true. True is equal to true. Condition is true. So the first condition is true. Let's check the second condition. What is the current value of turn? Turn is 0. 0 is equal to 1. The condition is false. Now since this condition is false, this while loop is going to break and process P1 is going to enter into the critical section. So that's why I said if someone is waiting in the entry section, then it is its chance next to enter into the critical section. So to summarize, the bounded waiting synchronization requirement is also guaranteed. What is the disadvantage of this Peterson solution? You see, all these three requirements are guaranteed. So this is the perfect solution that any programmer wants to implement to solve the problem of synchronization if multiple processes are trying to access the same resource. Now the disadvantage is, while doing the spin lock, that is busy waiting, it is going to take much CPU time. So it is a CPU bound checking condition, I can say, or CPU time is surely wasted in doing the busy waiting. But the advantage is, this mechanism is easy to implement in any programming language, C, C++, Java, etc. In my next videos, I will demonstrate this Peterson solution with the C# programming language. Alright. So that's how we reach to the end of this topic, Peterson solution. Remember that this is out of the three solutions that we discussed: lock variable, strict alternation, and Peterson solution. The Peterson solution guarantees all the three requirements of the synchronization mechanism: the mutual exclusion, progress, and the bounded waiting as well. So with this, I conclude this video. If you have any questions or doubt, feel free to mention in the comment box. In my upcoming sessions, I am going to discuss about the next synchronization mechanism, that is the semaphore. Semaphore is one of the important mechanisms used in industries also, because semaphore does not use the busy waiting statement, that is a spin lock, it does not use, but it uses the concept of blocking. And the blocking means it is certainly going to save the CPU cycle, means the CPU time will not be wasted at all by the semaphore mechanism.